this experiment, I used a AAA battery to demonstrate constant velocity using Newton's second law of motion. I used a AAA battery because it is a uniform object that, when applied a force to, moves in the same plane. I also used a flat, uniform surface to keep the battery in the same plane of the x-axis. In order for constant velocity in the x-plane to work, an object needs to move according to Newton's second law, which is seen here. Up here. So you have your v final equals your initial velocity you were moving at plus a certain force given to you, your net force, divided by your mass times your delta t. Now for constant velocity, there is no F net because F net causes an acceleration. So this whole part becomes 0, and your initial velocity is always your final velocity, which is what we were trying to prove here. So as you can see in Tracker, there are many things going on here, also being the constant velocity of my battery here. So I first had to set up parameters of I had use 30 frames per second. This is because I wanted more frames to be taken. If you have too few frames, your object's velocity may vary too much and your data will not be as exact as if you had many points. My delta t is also very small, so 0.03 seconds, and this is so I had a much smaller time interval, so my measurements for velocity would be more accurate. The less measurements you do, the more the velocity will vary, and the less linear your position over a time graph will be. I started my frame at 53 because this is when, after I pushed, I instilled initial force to the battery, this is when it finally achieved a constant velocity. I stopped the frame at 72 because it started to decelerate because it lost momentum, and I didn't want that to be accounted in the constant velocity. I also had to calibrate my battery, as seen here, using this blue calibration stick. It was about 0.01 meters, the battery's diameter, and this creates a distance ratio for Tracker to follow. So now it knows actually how long it is moving in the x direction because of that diameter. I also used the x-axis for the battery to be moving in the negative x plane. So as this ran, it also output data here, which is my experimental data. It also outputted a graph of showing how the position moved over the time. And as you can see, it's a very linear graph, negatively linear because it's moving in the negative x direction, which is what we hope to achieve. I then made a model to try and see if my experimental data matched up to a perfect uniform physics world data. So this is my Python model, and I created many initials seen up here, which help the code work. And this is a starter code. I had to put in the ball's mass, which is according to here, and the position vector, which was 0, where I put my axis, and I also had to find the initial velocity. So in order to find the initial velocity, you need to follow this, one of the variants of Newton's second law, and it's second distance minus your first distance over your time interval. And because mine was at 0, I just used my second distance divided by my time interval, and I got about negative 0.212 meters per second. So I put all the rest of my initials, and I also created a while loop, and I wanted the while loop to end when my Tracker file ended, which was about 0.6 seconds. Here I put my Newton's second law, and this keeps the code running new velocities per different positions until it gets out of the time loop there. So once it reaches the time it ends, it stops the loop and it stops the object from moving. So then we also have the position code, where after a certain velocity times time, you add more position to your initial position and it becomes your final position. So I will run this code, and you can see that it looks a lot like the battery, and it will also output a graph. So this graph I found in a CSV file and ended up using it on a Google Drive here, and I matched it up with my Tracker files. So orange is the perfect model from my Python data, and the blue dots are the files of my experimental data. As you can see, from 0 to about 0.03 or 0.3, I had near constant velocity, which was the hope for this experiment. Now, the rest of the experiment, my object started to decelerate, which, although not ideal, is going to happen in an experiment that was not in the perfect physics world. There were other factors to come into play, like the momentum slowly losing over time and the object losing that constant velocity, starting to slow down to a point where it would stop, or the fact that there were friction, air resistance, or other factors that do not make this exact. Um, If I were to repeat this experiment, I would use an object that constantly runs at a certain speed. This would eliminate the need to use a pushing force to get the object up to speed and decrease the possibility of the object decelerating. I was happy with the data I got, and I'm very glad that I helped demonstrate Newton's second law.